Welcome back. Let's now look at projectile motion. What do I mean by projectile motion? I mean things that, in this case, that go up must come down. Don't know if the blue is showing up very nicely. How about we go for an orange one? Okay, a nice orange. I think that shows up quite well, doesn't it? We go up. Everything that goes up must come down. Why? What's making this go down like that? Okay, up, down. Why? Yeah, that almost got away. Why? So when I throw it up, let's just look. Pretend now the ball is leaving my hand with a velocity. I have given it a push. All right? It could have been an impulse, an F delta t, okay, that gave it this velocity. But anyway, we give it, now it goes up. Up, 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 and at that point it comes down. Now let's examine what happens at the top. What happens? It stops and then comes down. So when we are looking at projectile motion, there are two distinct phases. Granted, there could be a bounce and then others, but essentially it is still an up and a down movement. So what do I always say to students? I say, guys, do yourself a favor. And when we say a project, oh, of course, draw it. Yes, always draw it. So we are doing projectile motion. So here we go. There goes our object up, and there comes my object down. You're saying, hang on, but you've drawn that as a parabola. It is a parabola. Okay? We just don't see it if we throw it up and straight back down. Okay? So let's just, I've just exaggerated the opening, let's say. Okay? We are only doing up and down. We are not doing that way as well. Okay? That was part of it, but it's now been removed, apparently. Okay? I'll do some in the A-level section. Okay, so what do? Well, quite straightforward. We say, right, step one, split this into up and down. When we are going up, we've got V initial here and V final equals naught. When we turn, V initial equals naught and V final equals whatever. It equals V initial, but don't get hung up on that because we're going to move the boundaries a little bit one way or the other now. So, just let's look. Now on the up, what is pulling it back? Come back here. What's pulling it back to Earth? Gravity, yes. So we say, right, acceleration is minus 9.8 meters per second. On the downside, what is acceleration here? Is it making it faster? Yes, acceleration is equal to plus 9.8 meters per second, right? So, we've said, draw it, split it into up and down, two separate pieces, and now we use Newton's laws of motion. Remember, just one last thing, time up plus time down is equal to flight time. Well, you'd expect that. If you take off from airport A to B, your total flight time is what you take going up, cruise, and down, correct? So the flight time is the total time up and the total time down. Now, we say, okay, put in what we're given and calculate what is asked for. You might have to go through a little bit of a few steps to get what you want. Now remember, Newton's laws of motion are given to you, all right? You have got V final equals V initial plus AT. V equals U plus AT. Okay, those are for people who are doing it under A-levels, O-level kind of thing. This is for the other syllabus. V final, V initial plus AT. It's the same thing underneath it, okay? We have got that V final squared equals V initial squared. V squared equals U squared plus AT. we've got that S or delta X is equal to V initial time plus a half a t squared. Right, S equals ut. I'll put it in for those of you who want it. S equals ut plus a half a t squared, and V squared equals u squared plus at. Okay. All right. S equals ut plus a half equal. Okay. V is equal, yeah. Pretty much. Yeah, that's about all we're going to use in this. Now, let's just have a look, all right? Because, Kevin, not AT. Sorry, my bad. I'm just looking at this thinking, you know, it's V squared equals U plus 2AS. Yeah, plus 2, plus V squared of U squared plus. Do you know what? Yeah, just stick around. Let me just check. Plus 2AS. That's right. 2AS, which is delta X for you guys. Yeah. 2AS. See, we all get confused with them. Okay, so now we got those. Those are all we're going to use. We're going to apply it up, we're going to apply it down, and that's basically all we get. Let's have a look at an example of this projectile motion stuff, right? Now, a couple of things to remember, just very simply, all right? Velocity here is equal to velocity there. Velocity up here is equal to velocity down at that point. The only thing that changes is the sign, okay? And you can decide upwards positive, downwards positive, depending upon what you're doing, as long as you've said what you're doing, okay? That's the key point here, is to say, okay, if I'm only falling down, downwards is positive, okay? Fair enough, that's cool, okay? So now, let us just take an example. Well, some of the favorite ones are the balloon problem, all right? We've got a hot air balloon is rising at 3 meters per second. Remember that if it's kilometers per hour, we change it to meters per second. So a hot air balloon is rising at 3 meters per second relative to the ground. I throw a ball vertically upwards at 5 meters per second relative to the balloon. Right. And whatever. Let's just start with this, shall we? Just move this up a wee bit. And let's just start. So what have they told us? They have told us that I am on a balloon. I am obviously in a basket, and there's my balloon. And I am going up at 3 meters per second. Okay, relative to the ground. The ground stays still. Okay, that stays still, right, because we're going up. Okay, and I throw a ball vertically upwards at 5 relative to the balloon. So I am standing inside the balloon here, and then I chuck that up at 5 meters per second to the balloon. What does it mean? We refer everything back to the ground, right? But if I am sitting still and I throw the ball up at 5, it is 5 meters relative to the ground. What if I'm traveling upwards on my chair at 3 and I still throw it with 5 relative to the chair? What's the actual velocity of the ball? It's 8, isn't it? So the velocity of the ball is 8 relative to ground. So what do we do? Well, first of all, we draw the path of this ball. Okay? I'm going to draw it from here. What does the ball do? Now, everybody initially thinks the ball falls out and falls down. No, it doesn't. The ball goes up for a short period and then falls down. Why? Because I'm throwing it up. It's got a velocity relative to the ground. Okay? If I was standing and I just dropped it, it would still be going up at 3. Think about it. I'm in the basket's going up at 3 and this falls out. What speed is this doing, velocity relative to the ground? It's traveling at the same velocity as the basket, which is 3, right? So it goes up a small amount and then falls down. If I'm on the top of a cliff and it rolls off, obviously it starts at 0, right? So yes, when I draw it, I have to say, hold on a bit. My ball is actually going to do that, isn't it? So now I say, okay. Okay, that's a height there. I said, right, split it up into up and down. So far, so good. Right. So if I'm going up and that other one is going down, next I said, right, I put in on my upside, acceleration equals minus 9.8 meters per second. And on the downside, acceleration is plus 9.8 meters per second squared. Okay? Then I say, right, V initial on the way up is equal to 8 meters per second. And V final is 0. V initial is 0 on the other side. Remember, I'm only looking at up and looking at down. Now, let's look at up. Let's say, how far up? How far up does it go? Well, let's see. Well, what do I want to know? I want to know the distance up. So I say V squared, V final squared equals V initial squared plus 2A delta X. So I say V final squared, I'm only looking at up now, is 0 is equal to V initial, which is going to be 8 squared plus 2 times minus 9.8 times delta X. Okay? And if I work that out, I'm going to end up with minus 64, which is that, divided by minus 19.6, which is equal to delta X, which is equal to 3.265. So then I go back to my drawing and put in what I know. I know that distance is 3.265 meters. All right? Please don't leave your drawings blank. It's like a geometry problem. When you are solving an angle, you get the angle, go to your sketch and put that angle in. Same as a circuit. If you've got a current, go there and put it in. A voltage or a resist, put it in. Okay? Don't leave it blank. If you leave your sketch blank, having worked it out, what's going to happen is your mind is going to see an unknown there. But it's not unknown. You've worked it out. Don't rely on your memory to say to you, I know it, therefore I've worked it out. Don't trust your memory. Just say to yourself, I'm going to write it on my sketch and I can forget about it. It works. Why? Because you're under time pressure in an exam. Okay? You don't want to have to remember stuff that's not necessary. The fact that you worked out 2 plus 2 equals 4, you don't have to remember 4. Just write it down. Okay? And put it in the right place. Okay? And how long did it take us to get there? Okay? In other words, what was the time to the top? So I go and I say V final equals V initial plus AT. How do I know? Well, V final is 0, V initial is 8 plus minus 9.8 times T. Therefore, the time up is going to be equal to minus 8 over minus 9.8, which is 0.82 seconds. So now I go back, I'm going to use green, and I say time equals 0.82 seconds to the top. Okay? Simple, isn't it? Okay? Simple, straightforward. What's the next step? The next step is to say, okay, all right then. Say they tell us that flight time was 4 seconds. So they tell us flight time 4 seconds. The question is, how high was the balloon when we threw it out? Okay, so they want to know how high was balloon when we tossed it. Okay. In other words, what do they want to know? They are looking for this, aren't they? Okay. Now, if you haven't drawn this, all right, you won't actually see what you're looking for. It will be a vague, fuzzy thing in your head. But if you've drawn it and working with it, it will be obvious that if I now work out the height from the top over here, top to bottom, I can subtract that from that and get the height of the balloon, can't I? Can you see the value of a drawing yet, or do I have to keep going over it? All right. Well, let's see. I'm looking for how high. So therefore, on the down side, I now say I've been given time from top to bottom. Okay, how long is it? They said the flight time was 4 seconds, right? Therefore, that's equal to time up plus time down. Time up was 0.82 plus time to fall down. Therefore, time to fall down is 4 minus 0.82 is 3.18 seconds. Now I can go back to my drawing, right? And I put on here, let me put it into, let's put it in blue, shall we? So now I say, right, time is equal to 3.18 seconds. Okay. Now I can say, okay, if that's 3.18, let's just get another page here. Okay, 3.18 seconds. What's my next? My next is to say, right, then what do I know? I know time is equal to 3.18 seconds. I know acceleration is plus 9.8 meters per second squared. And I know velocity initial was equal to 0. Therefore, what am I looking for? Delta x. I want to know the height. So what do I say? Delta x, whoops, not delta t. Delta x is equal to v initial times time plus a half a t squared. So delta x is 0 times 3.18 plus a half times 9.8 times 3.18 squared, correct? And my final answer is 49.55. Okay, 49.55 meters is that. Go up. So I go back and I put it in. All right, I put it in over there and it's blue, and I say my height is over there to there. Delta x is 49.55 meters. So how high is that? Well, it's obviously going to be 49.55 minus 3.265, isn't it? So h is equal to 49.55 minus 3.265, which is equal to 46.286 meters, and we would say above ground. Remember, answer the question the way they want it. Okay. Let's do one more, shall we? Let's look at this one. A ball is thrown vertically upwards at 3 meters per second, okay, from a rooftop as shown. All right, I'm going to do the drawing over here. All right, so it is thrown upwards at 3 meters per second, vertically up. So this is V initial, right? The ball is going to go up, and then it's going to come down, isn't it? Okay, it's going to come down. Just take that, disconnect that. It's going to come down, right? So now, okay, I say, okay, this is what's happening. This is up, this is down, all right? Okay, a person is standing 10 meters away, running at 3 meters per second to catch the ball. Will he or she be able to catch it? So what they're saying is the ball is going to come this way. There's a person standing, let's just say, there's a person standing over here, 10 meters away. And they're running at 3 meters per second, obviously in the direction of the ball, right? And they want to know, will they be able to catch it? Okay. Where do we start? Well, we start off with the ball because we can see which way that's going, all right? And we can see something there as well, all right? The velocity here is 3. There's no acceleration, so acceleration here is 0, all right? Therefore, V final over here is also going to be 3. As this person moves, they're not accelerating. Obviously, in the question, they might also put in an acceleration, but can you see by putting in the drawing and all the details, it's quite straightforward, isn't it? So we say, all right, we're there. All right. Now let's have a look. Let us start with up. Okay. Up, we said acceleration minus 9.8 meters per second. Okay. So how long to get to the top? You're going to get bored with me, but basically it's V final is equal to V initial plus AT. Therefore, V final is 0, 3 plus minus 9.8 times T. T in this case comes out to be 0.31. And remember, if you get a minus answer, just check your signs. They've just gone wrong somewhere there, right? So 3 seconds to the top. Okay. How high? Okay. So we say, how high did it go up? Once again, we do V final squared is equal to V initial squared plus 2A delta X. And we put in 0 squared is the final because Vf equals 0 and Vi equals 0 there, remember? Down is plus 9.8, A equals meters per second squared. So you can see we've taken the up. How high did it go? It went up 3 meters per second squared plus 2 times minus 9.8 times delta x, and you find delta x is equal to 0.46 meters. So now I can go back to my, my thingy, and I can say, right, time up was 0.31, and height was equal to 0.46. All right. And they told us the cliff was 20 meters high, so my bad, I didn't put that in, I apologize. They told us the cliff was 20 meters high. So now we know how long it took. Let's now work out on the downside, okay? Time again. Time to fall. How far is it falling? All right, it's falling, delta x is equal to 20 plus 0.46, right? Which is going to be equal to 20.46. Yep. And we plug into this formula here where we say delta x is equal to v initial time plus a half a t squared. So that's 20.46 plus v initial is 0. The time, okay, is going to be equal to t, okay, and a half plus a half times 9.8 t squared, okay, that's 0, Okay, it's going to be equal to that. So therefore, t is going to be 20.46, right, times 2 divided by 9.8, which is going to be 2.04 seconds. Because I must take the square root of that. Okay, so yeah, now I know. I say, but hold on a second. It's quite simple. I've got it, because how long is my ball in the air? I can say the flight time is equal to 2.3 is 2.04 plus 0.31 seconds, which is going to be equal to 2.35 seconds. So by the time the ball has gone from here, up, and down to the ground, right, that far, the person has got to have caught it. And yes, I haven't taken the height of the person into account. In other words, I'm saying they can dive and get it if they have to, correct? So now I say, right, this person has got, how long has they got? They've got 2.35 seconds. So basically, I have now said that time here is 2.35 seconds. All right? Well, what do I know on this person running? I know velocity is 3 meters per second, v initial, and v final is also 3 meters per second, no acceleration. I say delta x is equal to 10 meters. And I say, right, how long to run 10 meters at 3 meters per second? In other words, how long will it take this person to get there? Think about it. How long will it take the person? Well, it says time is going to be 10 divided by 3, which is going to be 3.33 seconds. In other words, no. They can't catch it. No, they cannot catch it. Because the ball is in the air for 2.35 seconds, right? I could also have said 2.35 and worked out how far he would run in 2.35, couldn't I? Same thing in essence, right? So yes, projectile motion is not a very difficult section, and it's only in one dimension, which makes it really, really cool. It's not a difficult issue. Now, how do we do it again? Step 1, draw it. Okay. Step 2, split it into up and down. Put in what you are told about the up, put in what you are told about the down. The next stage is to, even if it bounces off something, there's a nice question somewhere of it bouncing off something. And you start where you've got the most information and work forwards or backwards from that point. Remember, I could have started with the boy running and said he didn't catch it because, therefore, you'd have worked out flight time, etc., etc., etc. All right? So you just split it into the up and the down. Remember, what's pulling it back is gravity acceleration. So it's minus as it's going up, it's slowing it down. And when it turns, it's positive, so it is accelerating it. Okay? That is projectile motion. The next section is graphs of motion, okay? Which is a little more, taking a little more time. But have a go at those. They're pretty cool. They're pretty fun, actually. All right? But once again, seriously, and I know I have the same problem with our kids. Drawing it, yeah. You know, it's the only way, guys. Really and truly, it's the only way. Become the problem. Pick up a little car, use it. Pick up a ball like I did and look what's happening. That's the way you get into these problems. You get into them from there. Cheers. Have a great one. I hope that that mystified that. As I say, we're going to do more problems throughout the entire course that we're going to do. Cheers. Have a great one. Bye. See you again.